interpretations of subsurface structural geometry are fundamentally uncertain. So how do we reduce these uncertainties when making these interpretations? Well, one approach that's generally adopted is to deploy the use of section balancing techniques. In other words, can we restore our cross-section to show a geometry of undeformed rocks that is inherently sensible? We're going to explore these ideas by looking at the interpretation of one structure. And it's based on the sort of situation that we see in the photograph, which are anticlines that poke up above the surface in the edge of the French Alps. And our fundamental question is, what happens below the landscape here? What happens at depth? And the structure we're going to look at is based on this feature here, which is a rather nice open antiform. So what we see here is a group of people collecting field data, the shape of the folder outcrop. And this might be supplemented by subsurface information that's spatially restricted, such as boreholes, and we may have an image of part of the subsurface from seismic imaging. We then use that information to inspire a structural model, some kind of idea of what this structure might look like. And this is a hypothesis for the subsurface structure, and we illustrate the structural style on a cross-section, which is a two-dimensional slice through the structure. And this in turn will make predictions about the distribution of rocks in the subsurface and potentially other things too. Well, we'll come on to that as we go. So what section balancing does is test the geometries we see in our two-dimensional cross-section and demonstrate that these are geometrically, in other words, physically possible, to show that they are restorable. Some people would refer to this approach as validating the cross-section and therefore the structural model that lies behind it. So what do we mean by balancing? Well, for me, section balancing is a statement of strain compatibility, equal contraction for all layers. And this means that the edge of our model remains orthogonal. The left-hand side, the X on here, is a pin line. The right-hand side, Y, is a loose line. And the deformation has moved Y in to converge with X. And this contraction, this convergence, is assumed to be equal for all layers. And if we can analyze our cross-section and demonstrate that this is the case, the cross-section could be termed as balanced. Now, in many cases where people apply section balancing, simply they show the final state cross-section and the restoration together without much information about how it was created. It balances, it must be a valid interpretation. I want to take a different approach here, to use section balancing as a way of exploring different solutions, in other words, different types of structural models and their implications for a particular subsurface interpretation situation. So let's see how we go. As I mentioned at the start, we're going to illustrate this using a case study that's based on this anticline. And so let's look at what the input information is. And I've displayed this on a profile, in other words, a cross-section that's incomplete. It shows the amount of surface geology that we can directly observe or be reasonably confident about with minor projection into the near subsurface. It also shows information that we might get on an adjacent well that allows us to understand the stratigraphy at depths below that exposed outcrop. I've also shown a dashed line in here, which is a seismically imaged top of basement, if you will. So outcrop, well, and a top basement horizon from seismic. And these are the basic data that go into our structural model. So we're going to take a structural model and then draw the cross-section on the basis of this model, tied into the input observations. So the model we're going to use to start with is a buckle fold. Well, first of all, we can project some of the surface geology fairly uncontroversially into the near subsurface, like this, using the surface dips to constrain the continuity of the layers that we see in the fold itself. Okay, so now let's continue to draw the fold structure on the basis that it's a buckle fold. And we'll draw the fold up into the air and into the subsurface to fully define the geometry. So there is our cross-section. Now we need to test it, so we're going to see if it's restorable. For this, we will define a pin line on the left-hand side and a loose line on the right. It's really important to do this so we know between which points we're going to make our measurements. And they're common for all the layers that we're going to restore. Let's state our assumptions. We're going to assume plane strain. In other words, all the action occurs in the plane that we can see here, the plane of the cross-section. And this is, of course, a general requirement for section balancing. We're going to be more constrained than that. We're going to also assume that the bed length is conserved in the Tithonian, that light blue marker, and the Lower Cretaceous, dark green, and the other horizons too, from the cross-section to the restored template. In other words, there's no distortional strain in those layers. We'll talk about what happens in the rest of the Jurassic, that mauve unit, as we go. Another assumption we'll make is that the fold structure is detached on basement, in other words, along that thick black dashed line. And finally, we're going to assume the layers themselves are unfaulted. So we need to construct a restored template which shows the stratigraphy in its inferred undeformed state. And here I show the lower part of the Jurassic, the Tithonian and the Lower Cretaceous rocks, together with the top basement horizon that underlies all of them. And we're assuming that these layers originally had a constant thickness across the area that eventually becomes folded. In other words, the stratigraphy is layer cake. Notice that the layers that are above the Lower Cretaceous, which includes the Ergonian, are not constant across our cross-section at the top, and therefore we're not showing them on the restoration yet because we don't know quite where these variations will occur when we lay them out horizontally. And again, that hopefully will become more obvious as we go. So let's get going. First of all, we'll measure the arcuate length of the Tithonian around the fold between pin line and loose line, and we'll lay it out flat on our restored template. Let's do the same again with the darker green Lower Cretaceous horizon. Here, and again laid out flat on the restoration below. Now, let's turn our attention to some of the higher units, because the next unit up pinches out at the pin line and only achieves its main thickness as we go into the steep forelimb of the fold. But where is that on the restoration? Well, we need to measure around to that point from the pin line and report that measurement on the restoration, so the constant thickness of this horizon only is achieved to the right of that mark on the restoration. And now we can measure the distance that remains from that point round to the loose line. So now let's complete our restored template. We know that by the time we get to the loose line, the stratigraphy achieves these thicknesses, so we can draw in our thickness and then to pinch out at the pin, and we can report that measurement back on the template. So there's our restoration so far for the Tithonian, the Lower Cretaceous, and our next Cretaceous marker up on the restored template. There's a slight mismatch. Well, let's see how it plays out when we put the Ergonian on. So let's look at the Ergonian. It doesn't continue all across the section, so we need to measure for where it first appears from measuring in from the pin line to here and report that on the cross section below on the template. So this is where the Ergonian finally pinches out. Now let's recognize on the cross-section interpretation where the Ergonian achieves its full thickness, and that's inferred to occur at the crest of the anticline, where much of it's been eroded away. So that's where the full Ergonian thickness would have been originally. And again, let's find that as a measurement further along our units on the cross-section, and then find that onto the template here. Finally, we now need to measure the residue all the way around to the loose line, this distance here, plot it onto the template like that. So we have restored 4 formations, and they compare like this. So how's the loose line? Well, the loose line should be orthogonal to the layering, in other words vertical, on the restored template if all the layers have experienced the same horizontal contraction, and they're not. Our restoration shows a fairly common problem when you first attempt to restore cross-sections, particularly in folds like these. There's insufficient bed length at depth. In other words, the Tithonian is not long enough to match that length of the Ergonian, and so forth. However, does it mean that our buckle fold is an inappropriate interpretation? Well, I would argue that this mismatch is relatively easy to correct. A minor adjustment to our cross-section geometry above would fix the loose line and allow all our layers to have the same length on the restoration, particularly if we adjust the synform in here, essentially by increasing the outer arc length of the Tithonian. In other words, we need to pull that fold slightly down and to the right, which would increase the arc length around the folds, preferentially for the older parts of the units, increasing their bed length on the restoration. So a minor adjustment would fix the cross-section. But what about the older parts of the Jurassic on here that lie in the core of the fold and along our detachment? Well, we're going to look at its cross-sectional area for this formation. And if you put it out into a box shape, it's that cross-sectional area there on the right. Now what we need to do is to lay this out flat using its thickness on the restored template, the thickness that we count in the well. So simply dividing the square box on the right from the thickness of the Jurassic on the restored template establishes the length of strata in the restored template. And it comes right out to there. So there's far too much bed length in the rest of the Jurassic compared to those other units. And I would argue that minor adjustments to our interpretation couldn't fix the problem. So we've restored our cross-section, and we now need to ask whether it balances. In other words, has it passed the test? And pretty clearly, it hasn't passed the test. So what do we do in our workflow? We've collected and interpreted data. We've integrated these into a structural model and illustrated this in a cross-section. We've tested it, and our cross-section, and therefore presumably our model, have failed. So therefore, we need to modify something. We can either modify the section a little bit, or we have to go back and try another structural model. So let's apply a different structural model. And the one we're going to use is the idea that this fold structure is a ramp anticline. So again, let's build our cross-section. This part will be the same as the section we've used already. All the actions occurring in the forelimb of our fold. So let's draw it on. This time, we've got a thrust climbing from a detachment along the base of the stratigraphic units here, along the dashed line there, climbing relatively steeply across the stratigraphy, and then running off into the Miocene, the younger units, towards the left of the section. As a consequence, rocks have been lifted up to create the anticline that we see at outcrop. So in other words, we've changed an assumption that we had inherent in our first model. Rather than think of the layers as being unfaulted, we're showing the layers are cut by a thrust that climbs from the top of the basement. Okay, so we've illustrated a new model on a new cross-section, and now we need to ask, does it balance? So let's test it. Again, we'll transfer measurements onto our restored template. We can measure our length of Tithonian here, a length in the footwall, and a length in the hanging wall, and put them together to reach the loose line here. I've marked with a blob along there the position that the thrust occurs when you unravel the strata. Let's do the same now with the dark green lower Cretaceous rocks, here on the cross-section and here on the restored template. These are beginning to match up quite well. Well, let's continue. So now we need to do a measurement in the next Cretaceous unit. Again, this is going to be a wedge shape that we'll have to build as we go. But we can start off by measuring the distance in to the thrust, to here. And within that footwall panel is where that stratigraphic unit is tapering. Beyond it, to the right, the Cretaceous unit retains constant thickness, which is within the hanging wall of the thrust. So let's measure the hanging wall length back to the loose line and put it onto our restored template here. Again, there's that distance that the bed restores to. Finally, let's look at the ergonian. And in this interpretation, we're saying there's no ergonian preserved in the footwall to the thrust at all, presumably it's been eroded away. And the ergonian is exclusively found in the hanging wall. It's tapered as it approaches the thrust plane, but as you go over the crest of the fold and back towards the loose line, the ergonian has a more constant thickness. So we measure in the footwall distance where the ergonian is not and put it on the restored template. That corresponds to where the thrust is as well. Now let's measure to here, the distance around in the hanging wall to the thrust to where the ergonian achieves its normal thickness, that distance there, and then finally the distance from that point on the crest of the fold back to the loose line. Put the template on, measure that distance, and plot it onto the template. So That's the Argonian restoration. How's this stacking up? Here are all of them together. And that's not a bad match, is it? Let's put our loose line on. It's a bit wiggly, so a minor adjustment is needed in there to change the length a little bit. So very minor adjustment to the section would fix this loose line. We can keep running with it. But now, what about the rest of the Jurassic? And again, we're going to conserve the cross-sectional area that we see on the cross-section itself at the top and report that back onto the template below. We can think of this as an excess area restoration. So the total cross-sectional area above the dashed line, above its regional there in the core of the fold, largely in the hanging wall to the thrust, is the area we need to consider, and it's that rectangle over there on the right, and we need to pop that onto our restoration below here. So that's the excess area restored. That's the restoration. And I would argue that just a minor adjustment in the fold structure in here would allow the slight excess length of the rest of the Jurassic to match the other bed lengths in the higher parts of the stratigraphy. It's looking pretty good. So let's now add the thrust profile onto our restoration. I've just put the blobs on there where the thrust was encountered in our measurements for the Tithonian Lower Cretaceous and Younger Cretaceous strata, as those blobs through there. And now to find its distance where the thrust climbs off the top basement, we measure along the top basement to that point there and report it back onto our cross section. So we can then join that all up to put the thrust trajectory in. It runs as a flat along the top basement and then climbs a ramp through those points identified on our restored template. That's model 2, the ramp anticline. It hasn't quite balanced yet, but it's on the right path, and with some minor adjustments, I'm sure we could make it work. So the ramp anticline model has a very good chance of being restorable and therefore a valid interpretation. So you might argue the job's done. We've collected and interpreted some field data, we've applied a structural model, the ramp anticline, we've illustrated it on a two-dimensional cross-section, we have then tested it by restoring it. We've seen that it restores to a geometrically, physically possible state, in other words, some stratigraphy that we see on the template in there. So our cross-section and therefore the structural model has passed the test. And conventionally you might rub your hands and say the job is done. We've finished, we can move on to a different example. But of course, just because we've got one structural model that's passed the test, it doesn't mean that all other models will fail. So of course that means that we can take our existing workflow and we can spin around and create a new structural model and illustrate that on a cross section and test that one. So we can go around these loops many times, trying different ideas out. So let's try another option. And we're going to challenge the assumptions. And the key one we're going to challenge is the idea that there's detachment along the top of basement. In other words, we're going to apply a new model, model 3 we're calling here, which is about structural inversion. Let's build the cross section. And you may recognize what we're doing here. So we've built the back limb and we're actually creating the buckle fold geometry for the layers of Tithonian and Younger strata. But what we're going to argue is that top basement marker has been offset. So let's put our restoration back from what we did before. We know how this is going to play out for the Tithonian and Younger rocks. Put our loose line on and put our measurements on. The Tithonian measurements, well, let's just put them all on again. So there is our loose line for our restoration, and we did this for the buckle fold geometry. We argued that a minor adjustment of the sin form within our folds pair in here would allow the loose line to be more robust and essentially orthogonal to the strata. But we're still left with this problem of the rest of the Jurassic. So that's the cross-sectional area for the Jurassic rocks that are older than the Tithonian and overlie our detachment between the pin and loose lines. Let's put the loose line onto our template. So we're retaining the loose line and pin. Now, of course, as shown on the template below, there's insufficient lower Jurassic rocks. But rather than allow the loose line to be broken and pushed off to the side, let's retain the cross-sectional area and put it here, below the fold. In other words, we're saying that the core of the fold structure is made by the fill of a pre-existing half graben that has been pushed back up as the pre-existing normal fault has been reactivated in contraction. So let's put that structure onto the cross-section. Even though the top basement marker joins up now, in the pre-thrusting state it was offset, and what the contractional tectonics has done has recovered the extensional offset and restored it so that we have what is called a null point, where there's no net offset of the top basement marker. So we can argue that the basement horizon, even though it is continuous now, has a history so that it has no net offset in the present day state. That is a common behavior in inversion tectonics. So where does this leave us? Well, we've been around the workflow. We've applied a structural model, inversion tectonics, we've illustrated it on a 2D cross-section, and we validated it, and it works. In other words, it's restorable. Our template isn't a layer cake template, but it shows geologically reasonable geometry. A half graben overlain by post-drift sediments of Tithonian and Younger Age. So you can go around the loop several times. Just because a section balances doesn't mean it's a unique interpretation. Each new model and restoration that passes makes different predictions, not only for the structural geometry that we see in the cross-section today, but also for the pre-existing template, in other words, what the stratigraphy looked like beforehand, and also the amount of orogenic contraction that the structure has accommodated. So many different structural models and cross-sections may balance, but they make different sets of predictions for contraction, previous stratigraphy, and structural geometry. So that's an illustration of the application of a balancing and restoration workflow to build structural interpretations. For me, it's the most useful thing about section balancing, and often you learn more when a section doesn't balance. It allows the interpreter to explore options and alternatives when they come to consider what subsurface structure might be. You can have conventional models and discriminate between them, but it's worth challenging some of the assumptions and try alternatives.